Right, welcome to lecture number 4 in our revision series for EIR 221. So this lecture actually only covers one part of chapter 4, which focuses on superposition, source transformation, and then the so dreaded Thevenin and Norton equivalent circuits. So all of these principles are interconnected with each other, and we need to look at those. And again, these are techniques that we use to solve for a certain unknown in a circuit. Everything we do is just simply techniques that we use to solve for a circuit. So in this part 1, we are going to focus on on superposition, what it is, source transformation, which is effectively going from Thevenin equivalent to a Norton equivalent or vice versa. And then we're going to do quite an extensive 2 examples on how to find the Thevenin circuit, and then in part 2 we will do an example on how to find a Norton equivalent circuit. Let's first just look at the definitions for linearity and superposition as you've learned in physics many moons ago. So what is a linear system? It has to satisfy 2 conditions. The first is the additivity condition, where if we add 2 variables or stimuli, x1 and x2, and we plug that into a certain function, it must equal the sum of the 2 functions where we only put in 1 variable in the function at a time. Then the homogeneity condition, the homogeneiteitsvoorwaarde, there if you multiply your stimuli or your variable x with a constant a and you put that into your function f, it must equal the same as just x in the function, and then you multiply the result with a constant a. That's a linear system. Superposition is the net response of a linear system caused by 2 or more stimuli is the sum of responses that would have been caused by each stimulus individually. Now, how does this apply to the context of circuit analysis? So how does linearity apply in the context of circuits? So the linear circuit is one, where's my pen, whose output is linearly related or directly proportional to its output. Now, a perfect example of this is just a resistive circuit. We know that V equals IR. So we know that V and I is directly proportional with a ratio of the resistance. And we know that if we looked at earlier in the first lecture, we had this graph. We've got I and V, and that's supposed to be a straight line, kind of straight line. So that gives you a linear relationship. Then in general, the circuit is linear if it obeys the homogeneity and the additive properties. What does that mean? This very difficult English word, homogeneiteits, real, meaning that some constant multiplied on both sides. So we know that Ohm's law is linear, but then if we multiply either the voltage or the product of the current and the resistance with a constant K, the equation still holds. Then in terms of additivity, here you've got 2 currents. So if you add current 1 and current 2 together and you multiply that with a resistance, it's the same as taking first current 1 multiplied by the resistance, then we add the current 2 multiplied by the resistance, and that gives us a V1 and a V2, of which the sum is still the total resistance. How does superposition apply within the context of circuit analysis? So the superposition principle states that the voltage across, or the current through an element in a linear circuit, is the sum of the voltage across, or the currents through that element, due to each independent source acting alone. Very important, each independent source acting alone. In other words, we take one source at a time. So superposition helps us to analyze a linear circuit with multiple independent sources by calculating the contribution of each source separately. So again, superposition is a technique like nodal analysis, like mesh analysis, that we can use to solve a circuit. It's just another tool in our toolbox. So how does the process of superposition work? Number 1, there's my pen. Number one, you turn off all independent sources. You can only turn off independent sources except one. And then you find the output, whatever it is that you're looking for, a voltage or a current, due to only that active source, the one that's still on, using the techniques that we did in chapter 2 and 3, all those tools. Then you repeat that step number 2. So step number 2, you repeat step number 1 for each of the independent sources, and finally you add up your different results to get the final result. So at the bottom picture, we want to solve, red is so intimidating. We want to solve for the voltage V over there. But we've got two sources. We've got a 3 amp source and we've got a 6 volt source. So now we take one source at a time and we need to zero all the rest. So in the first one, we solve using the 6 volt source. So what do we do with the 3 amps? It becomes 0 amps. What is 0 amps? 0 amps, as you can see here on the right, is an open circuit. In other words, there's nothing there. Current source, when you zero it, becomes an open circuit. And then plus, when the voltage source becomes 0, it becomes a short circuit over here. So what can we do? So we need to solve both. So we need to solve circuit number 1 and we need to solve circuit number 2. Circuit number 1, the easiest we can do here is, well, they're using mesh analysis. I would have just done voltage, a voltage division through this one. So I would have said V1 prime in this case is going to be 4 over 4 plus 8 times 6, and then you get a certain value. In the case of circuit number 2, I would have found I need V2 over there, but the current, this 3 amp current is going to split up into two different currents. It's going to go I2 and it's going to go I3. And if I have I3, I can find V2. So in this case, I know that V2, well, it's called V2 equals I3 times the 4 ohm resistor. That's a times the 4 ohm resistor. But how do you find I3? You can do a current division. Where am I going to write down this part? So we can write down I3 equals the other resistor, 8, divided by the sum of the two resistors, which is 12, times the total current, which is 3. So in that way you can find I3, and once you've got I3, you can plug it into that equation, and then you can find what V is, and in the end, what is V? V is then V1 plus V2. Right, so in that way you take one source at a time, solve the circuit, and you get the total result. Source transformation. What is source transformation? That is the process of replacing a voltage source, Vs, in series with a resistor R by a current source, Is, S for source, in parallel with that same resistance, or vice versa. So as you can see here, so in this case we're going from a voltage over to that side, we're going from voltage. So this circuit over here, as you will see, this is a Thevenin circuit because it's a voltage source in series with a resistor, and on this side there's a current source parallel with that same resistance, and this is known as my Norton equivalent. So the two types are simply related through a source transformation. How do we convert from the other? How do I calculate Is? So in this case, Is would simply be, we would calculate that as Vs divided by the resistance. And in this case, if you want to know what Vs is, we would calculate it as Is times the resistance. And that's the simple and quick way on how we do a source transformation. And again, it's a technique that we can use to change or alter a circuit diagram so that we can solve it more easily. In other words, just like you would parallel two resistors or series two resistors and add them together. Now you can do source transformations to simplify your circuit so that you can zoom in on the part of the circuit that you actually want to solve. Talking about Thevenin and Norton theorems, why do we do it? So why do we want a Thevenin circuit? Or why would you want a Norton equivalent circuit? So in this case, we assume that we have a fixed circuit but with a variable load to it. In other words, where's some space that we can draw it? So let's assume you have some fixed circuit. What happens in that box, we have no idea. There's a lot of circuit elements in that box that we don't know, but then this circuit has two output terminals, and to this we connect a variable load that can vary. Some R that varies, and what we want to find out, for instance, is what is the power dissipation in that resistance. Now we don't want to solve this big question mark circuit diagram every time just to find out what the power in that resistance is. So what we do is we want to separate the fixed part. So now we're at the third point over here. We want to separate the fixed part of the circuit from the variable part, and we analyze that only once. And then once we have solved the fixed part, we've analyzed the fixed circuit, that is replaced by an equivalent source resistance, which is the Thevenin equivalent resistance, or with a current resistance combination, or a Norton equivalent, depending on which one will solve your circuit easier. So then usually we do a Thevenin equivalent circuit. But then you have a very simple, if you do a Thevenin equivalent circuit, we replace the question mark simply with a voltage source, and then there's some Thevenin resistance, and then we have our two terminals, and we still have a variable resistor in there. So then this becomes R Thevenin, and over here we have V Thevenin, and now it's much easier, this is our load resistor, to solve that circuit than when we had the complex circuit in this box over here. Right, so the whole box question mark gets replaced with a very simple circuit, which is then easy to solve in order to find the power or the current, power in the resistor, the load resistor, or the current flowing through the resistor, or the voltage across that load resistor. So what exactly is Thevenin's theorem? Thevenin's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source, V Thevenin, in series with a resistor, R Thevenin, where V Thevenin is the, this is now the important bit, where V Thevenin is the open circuit voltage at the terminals, and R Thevenin is the input or equivalent resistance at the terminals when the independent sources are turned off. Right, so now you can see why did we have to talk about superposition, because in superpositioning we turn circuits off, and now to find the Thevenin or Norton equivalent circuit, Thevenin circuit, we need to turn the independent sources off. So here we've got, I said this is my question mark, my two-terminal circuit, which I don't know what it looks like. There's my two terminals A and B. There's some load in here, which is could be some resistor, variable resistor, and that we then replace by V Thevenin or R Thevenin, with which we can then quickly solve the circuit. How do we actually find the Thevenin equivalent circuit? What we need to do is to first, so number one, you calculate the open circuit voltage at the terminals. So here we've got terminals A and terminals B, and we need to find the open circuit voltage of at those two terminals of this big two-terminal circuit. Once we have that open circuit voltage, that open circuit voltage then becomes my Thevenin equivalent voltage. So how do we solve the circuit? Using all the techniques that you've learned up till now. Ohm's law, Kirchhoff's voltage laws, nodal analysis, mesh analysis, might have to use superpositioning or source transformation. So all those tools we'll need to get out. Then step number 2, in finding the Thevenin circuit, we need the Thevenin resistance. For that, we need to set all independent sources to 0 and then find the resistance when looking in. So here we are looking into the circuit, and I want to know what resistance do I see between terminals A and B when I look into this circuit. So now it becomes important whether you can do series and parallel. So very important, note, a zero voltage means a short circuit. 0 volts is a short circuit. A zero current is an open circuit. In other words, you can't have current flowing in an open circuit. There is no conductor for the current to flow in, so it is going to be 0. So you have to keep this in mind when we're making the independent sources 0. Last thing before we get to an example in getting Thevenin's theorem is there's a bit of a snag when having to calculate R Thevenin and you have to zero the sources. Two cases. Case number one is where you don't have any. You have no dependent sources. That's the easy version. Then you simply just turn off all the independent sources. Current sources becomes an open circuit. Voltage sources becomes an short circuit. And then you calculate R Thevenin, because you're going to be left with a lot of series and parallel combinations of resistors. The second case is not so simple, because what happens if you've got dependent sources? And in this case, you're going to use Ohm's law. How do we do it? We turn off all the independent sources as we would, and then we apply an imaginary voltage source, V0 equals 1, at terminals A and B. Why a 1 volt source? Because if we look at this equation, it just makes using Ohm's law a bit easier. If you've got 1 divided by anything, or the current that we're going to get, you just get the inverse and we have R Thevenin. So then, once we've applied this imaginary voltage source of 1 volt, we plug that into our between terminals A and B. Then we determine the resulting I out at the terminals, at the output terminals, flowing because of this VO, and then we use Ohm's law to calculate R Thevenin. So now I'm going to do 2 examples, the one for case 1 and one for case 2, to illustrate these principles. Right, so here we've got example number 1 that we're going to look at. There's no dependent sources, only independent sources, and we want to find the Thevenin equivalent for the circuit between terminals A and B. So what do? First, we want to find V Thevenin. How do we find V Thevenin? We do an open circuit. So if we do an open circuit version of the circuit, what are we going to have? We're going to have plus minus. Let's draw the circuit in black. So then we're going to have our plus minus, and this is 12 volts. And we're going to have our 6 ohms. And there's going to be the current source, which is over there. There you go. And there's another 6 ohms sitting over there. And our 4 ohm resistor sitting over there. And then we're at terminal A and terminal B. So we want the open voltage. So what are we looking for? Actually, VAB with a plus and a minus. And there's a 4 over there, 6 and a 6. So how do we find the voltage VAB? So now you have to choose. We've got multiple methods in terms of mesh analysis. You've got nodal analysis that you can use to find that voltage. What in this case is going to work the best? I'm going to use mesh analysis. Why? Because if I make this my reference node and I call this V1 and I call this node, so nodal analysis, V2, then V2 is going to be my VAB. So I just need to solve for V2. And I already have a current. What's the current again? Oh yeah, 2 amps. And when you use nodal analysis, then you're looking for currents. And I have a current source over here. I know what the voltage is at that point. I know it's going to be 12 volts because I've got this 12 volt source between my reference node at the bottom and this node at the positive node of the 12 volts. So I'm just going to use nodal analysis to solve for V2, because this means that B is at 0 volts. So there is 0 volts because that's connected to my reference node, and my A terminal is connected to V2. Right, so let's write down the Kirchhoff's current law. So we're going to write KCL at node 1. So what do we then get? So we're going to say all the currents that comes out of a node is going to be positive. So we need currents that goes out. So I'm going to write a current that goes out, and there is a current that has to go out, and another current that goes out. So writing that, the first one going through the 6 ohms, I'm going to write it's V1 minus 12, because it goes to the 12 ohms, divide by 6, plus current going down through to the reference node goes through 2 amps, but they're in opposite directions. So that current becomes minus 2. And then plus the current that flows from V1 to V2, and that flows through a 6 ohm resistor, and that must equal 0. So I'm just going to multiply this whole story with 6, which means I'm going to have V1 minus 12 minus 12 plus V1 minus V2 must equal 0. So if we simplify this, I've got 2 times V1 minus V2 must equal 24 in this case, and we will call that equation number 1. Right, then if we write down Kirchhoff's, now that's all I need actually, because let's do that still like this. All right, so KCL, I was just looking at thinking something else. We actually don't need to solve for V2, and you'll see just now what happens. All right, so then at node 2 you've got a current going down that way, and we've got a current going down that way. I'll just show you the 2 different versions. We can do both ways. Alright, so let's write down that Kirchhoff's current law. So there we've got V2 minus V1 divided by 6 plus the other one, which is V2. Why did I write 2 there? Sorry. Not a V2 there. I need a V2 over here. V2 minus 0 over 4 ohms, come on, 4 equals 0. So what are we going to multiply out? Yeah, that's 4 and 6 times. We'll have to go with times 12 on both sides, through the out, so that becomes 2 V2 minus 2 V1 plus 3 V2 equals 0. So how many V1s do we have? We've got minus 2 V1 plus 5 V2 equals 0, and that we will call equation number 2. Okay, so let's just draw a line down here. So what can we do? What are we after? We're actually after V2, so we are simply going to say equation number 1 plus equation number 2, because that's going to cancel out my V1s. So that will give me 4 V2 must equal 24, which means V2 equals 6 volts. And hence we know that VAB equals V2 equals 6 volts. So my VThevenin equals 6 volts. Right. The other option, when I was hesitating there, what I wanted to do there is we could also write V2 just based on V1. We actually only needed to solve for V1 because we know what V2 is. It's going to be the current that flows from V1 through the 4 ohm resistor. So that would have been a little bit of a different technique. In other words, we could have rewritten node 1. So this is now a bit of a different version. So at node 1 we could have simply wrote V1 minus 12 divided by 6 and then minus the 2, and then we could have simply written V1 minus 0 because now the 6 ohms and the 4 ohms is in series. 6 plus 4 equals 0. And then so from this equation you could have solved for V1. From V1 you could have used a voltage division to get to VAB or V2, because then you would have gotten that V2 must equal V1 times 4 over 4 plus 6. So in that way you would have solved for V2, and that would have resulted then, or let's write it down, that from V2 you effectively then have your VThevenin. Alright, so that's just a different method that you could have used to solve for the Thevenin voltage. Alright, so now we've solved for the Thevenin voltage. In the next we need to solve for the Thevenin resistance. So we continue with example 1. What we want to do next is find the Thevenin resistance. So now we need to zero the sources. So what is this circuit going to look like? The 12 volts, a voltage source, becomes a short circuit. So the voltage source disappears. Then we still have the resistance, the 6 ohms. Then the current source becomes an open circuit. So that we can just draw it like this. It becomes an open circuit. Then we have the 6 ohms, the other 6 ohms. Then we need the 4 ohm resistor over there, and then we are at terminals A and terminals B, and we want to look into these two terminals A and B and then find out what is the resistance between those two terminals when looking in. So how does this circuit now connected? What is series? What is in parallel? We have, so what do we have? R Thevenin was then equal. Now we're working from left to right. So let's work in this direction. We're working towards terminals A and B. So we've got two 6 ohm resistors in series. So it's 6 plus 6. They're in series. Then those two are in parallel with the 4 ohm resistor. And that's all there is. So what do we have? We've got 12 ohms, so we've got 1 over 12 plus parallel with 1 over 4, all of that minus 1. So that means we've got 1 over 12 and 3 over 12, which is 4 over 12, which is 1 over 3, which is 3 ohms. I hope you followed. Okay, let's just write that down. So 1 over 12 plus, to get this to 12, I need to multiply by 3 at the top, inverse So that gives me, if I add at the top and I just inverse the thing so long, I get 12 over 4, which then gives me 3 ohms. So what does the Thevenin equivalent circuit look like? I've got a plus minus source in series with a resistor between these two terminals, and my Thevenin resistance is 3 ohms, and my Thevenin voltage we calculated as 6 volts. And now we can reconnect our 1 ohm resistor through which we want to find the current I flowing from terminals A and B. And now you can see it's simple, because now it's just going to be 6 volts divided by 4, which is, what is that now? 1 and 2 over 4. So that's going to be 1.5 amps flowing through the 1 ohm resistor. So in this case, the 1 ohm doesn't see the difference. All it sees is terminals A and B, and whatever is beyond those two terminals for the 1 ohm is exactly the same. What would the Norton equivalent look like? The Norton equivalent would be a current source pointing in the direction of the voltage rise towards the positive terminal, but that would be parallel to the resistance. So the resistance stays 3 ohms. So where's my terminals A and B now? There's my terminals A and B. So now we're drawing the Norton equivalent. What will this current be? You take the volts, divide by amps. So what is this? How can I write this? So this equals 6 divided by 3, which is 2 amperes. So that is my Norton equivalent, or a source transformation of my Thevenin equivalent. So that's just an easy example on the basics of how to find a Thevenin and Norton equivalent for using only independent sources. In our next example, which is a little bit more complicated, we are going to look at a circuit that actually has dependent sources in it. So we're going to need to follow a number of steps now. It's to actually solve this circuit. So first we're going to solve for our Thevenin. My pen will just work along. So we need to find our Thevenin. So what is the steps in solving for our Thevenin? Step 1 is we need to zero all independent sources. All right. But in this case, there is only one independent source, which is this 3 volts that's sitting there. And how are we going to zero that one? We're going to make it a short circuit. But now there's also 2 dependent sources. We've got 2Vx and we've got a 40IO, both of them dependent. So it's not as simple as the previous example where you can just calculate a bunch of resistors in series and parallel. So the other thing that we will have to do is we'll have to insert a imaginary 1 volt source between terminals A and B. Between A and B. Terminals A and B, so that we can calculate our Thevenin. So what is this circuit going to look like after we've done these 2 things? So we need to redraw our circuit diagram a little bit. So if we redraw it, so our voltage source is now 0, so we draw in a short circuit. There's my short circuit, very nice straight line. Sorry. Then we still have our 1 kilo ohm resistor sitting in there. We then still have our dependent one dependent source. So why am I redrawing the circuit? It's just always safer for me to redraw the circuit whenever I solve it. I know it takes a bit of time, but that's just safer for me, because then I have my original circuit at hand always. Then I have my current source there, dependent current source, which is 40 times IO. Where is IO? Oh, IO is flowing here on the left hand side, and this is 1 kilo ohm sitting over there. Then all of this current source is parallel to a 50 ohm resistor, and that is then connected to my terminals A and B. And what I now need to add between these two terminals is my plus minus 1 volt source, and from this 1 volt source is going to flow a current Ix. So R Thevenin in the end, Ohm's law, will have to be volts. So my 1 volt divide by Ix. So Ix is the actual value that I need to solve for. Well, so there's just one other variable that we need to put in here, and this is that plus minus Vx, because that Vx is going to dictate the dependent voltage source, voltage controlled voltage source voltage. Alright, so let's see what we can solve first. We need either Vx or IO. Now looking at the circuit diagram, we can see that Vx must equal 1 volt. Why am I saying that? Because Vx sitting over here, so the Vx sitting over here, over there, is parallel to my 1 volts that I put in there. So Vx has to be equal to 1 volt because they're parallel, they're on the same node there, and they're on the same node over there. So both of them has to be 1 volt. With that being said, it means we can calculate IO. Why? Because IO is simply 2 times Vx divided by 1000. But now be very careful here. According to this source, the direction of the current is going to be counterclockwise, because the current has to flow out of the positive terminal. Which means because of that, we need to put in a minus in there. So it's minus 2Vx divided by the resistance. So that gives me 2 volts divided by 1000, which is then obviously minus, don't forget the minus, minus 2 milliamps. Fantastic. Now that we've got the minus 2 milliamps, we can plug this, so the 2 milliamps can now go into that 40 IO. So then we know what that current source is going to be. Now how are we going to solve for Ix? Now in this case we're looking for currents, and I'm going to use in terms of I want to solve for currents. I know what IO times 40 is. So I know, let's just draw in a different color here. Blue. Yeah. So I know what this current is because we can calculate that. 40 times the minus 2 milliamps. I can calculate the current that goes through the 50 ohm resistor because it's just Vx divided by 50, Ohm's law. And then the only unknown is Ix that we need to solve for. So I'm going to write down Kirchhoff's current law. I'm going to keep it now in blue. So if we write down Kirchhoff's current law at that node, what do we have? All the currents coming in must equal the currents going out. What currents are coming in? Ix is coming in. That must equal the currents going out, which is 40 IO, and then the current going out is Vx divided by with 50 ohms. So what is that equal to? 40, what is I0? It is minus 2 times 10 to the minus 3 because it's in milliamps, plus, what is Vx? I know it's 1 volts because I put it there, divide by 50, and that equals, if I calculate that on my calculator, I get, where's my pen now? I get minus 60 milliamps. Sorry, just fits in there. So now I know what Ix is. In other words, I can go back and complete my equation. So if I now take this value, I need a new number, new color. I now want to plug in this value into this equation. So if we complete the equation, that now means that R Thevenin equals 1 over minus 0.06, which equals, if we just take the inverse, minus 16.6 repetitive ohms. Alright, now you might go, wait a minute, I've got a negative resistance. It's not possible to have a negative resistance. But remember, there is 2 dependent sources in my circuit. So in this case, I can actually have a negative resistance when I've got dependent sources, which is actually then providing me or generating energy. Oh, sorry, not generating energy, they're actually generating power. Alright, besides using Kirchhoff's current law to calculate Ix over here, you could have used any other analysis techniques. You could have used a nodal voltage analysis, you could have used mesh analysis. In my case, it was just simply a case of I know 2 currents, I only need the 1 current coming in, so I opted for just using Kirchhoff's current law. So always remember to try and aim at using the easiest, simplest method available for you to find the answer. Right, so the final answer then that we were looking for is R Thevenin over there. So we're not done yet. Next we need to figure out what is the Thevenin voltage of the circuit. That we'll do in the next slide. So next, what we want to find is the Thevenin voltage between terminals A, B. So where's the Thevenin? Here we've got plus minus VAB, but that is also I Thevenin voltage. So next what we want to do is find V Thevenin, which equals VAB, and if we look at the circuit, it's the same polarity as Vx, so this equals Vx. So what do we actually need to solve for? We need to solve for Vx. Now I'm going to do it in a combination style. After this slide you will find a step-by-step procedure to solve the same example using techniques, but I want to show you how do you simplify solving a circuit by just getting to know the circuit and solving it. Alright, so what we want to find is Vx. How do we find Vx? So if we look at on the right hand side and we follow this 40 I0 current, this current is going to flow in a counterclockwise direction through that 50 ohms. Can the current go to the left in this case? In other words, can it go in that direction? To answer that question, let's look at on the left hand side loop. So in this case, if we draw, just draw another color. If we draw this clockwise loop, we've got I0 flowing everywhere. So this loop is going to be I0. And when I0 gets to this point, it's I0 coming in and it's I0 that goes out at this point. And Kirchhoff's current law says what goes in must go out. So if it's IO coming in and it's IO what's coming out, how much is flowing over here? It has to be 0 amps flowing in this leg at the bottom. So there's nothing flowing there. So all of this 40 IO that's flowing has to go through the 50 ohms. But now notice this is going to create, because the current direction of the current is counterclockwise, it is going to create an opposite polarity, plus minus across that 50 ohm resistor, which is opposite to Vx. So if you keep this in red, what we can write down in our right hand loop, so let's write right, and on the right hand part of the circuit we can write down that Vx, which is what we're looking for, Vx must equal minus the 50 ohms times 40 IO, which is then minus 2000 IO. Again, why the minus? It's because if we follow the direction of that 40 IO, it goes in at the bottom of a resistor and out at the top. It creates a voltage drop across the resistor. It enters the positive and then goes out the negative. So that is the opposite of Vx. On the left, let's keep it green. So on the left, because now we've got an equation with two unknowns, so we're gonna need another equation that we're going to get from the left hand side. And then I'm just simply going to use Kirchhoff's voltage law. What did we use here at the top? On the right hand we basically just used Ohm's law. Now we're going to use Kirchhoff's voltage law here at the bottom. And we start at the minus 3 volts. Then we move through the 1000 ohms plus 1000 times IO, because the IO creates a voltage drop. If you just look at the resistor, plus minus across that resistor. Then we go in at the positive terminal of the voltage controlled voltage source to Vx, and that must all equal 0. So again, if we write it in terms of what is, now we want to calculate Vx, so what is IO then? This means that we can write that IO must then equal minus 2 Vx. Let's make this V a little bit bigger. Vx plus 3, all of that, divide by 1000. Right, so this is equation number 2, and there at the top we have equation number 1. So now we want to substitute. We're going to put 2 in 1. So what do we have then? We've got then Vx must equal minus 2000 multiply, what is IO? IO, we saw it was minus 2Vx plus 3 divide by 1000, which means that minus is going to become a plus, these two minuses, the thousands cancel out, so that 1000 disappears and we're left with 2. So we are left with 4Vx plus 2 times 3 is 6, and this means this Vx goes over. What's wrong with the signs now? Somewhere I made a mistake. Oh, yeah, here it is. This minus of the 2000 that I have over here, let me just get out my red marker pen here. This minus, we didn't multiply that into the plus 3 over there. So this plus 3 needs to become a minus. So let's just scratch that out. So number 1, F4, So this is going to become this. Let's scratch that one out, and that one, and that one, and that one. So let's keep it as it was. That was a minus. Oops. Was a minus. Just don't want a thick minus like that one. This was a minus 2000. We had a minus 2Vx and we had a plus V3. So the minus 2 times the minus 2 gives me the plus 4, but the minus 2 times the plus 3 gives me a minus 6. Right. So then what do we get? We get minus 3 Vx equals minus 6. And hence, what do we have? Let's just rewrite the bottom over here. So finally, what do we have? We go back to, that means hence Vx equals 2 volts, which means Vthevenin equals 2 volts. So can we then draw our final circuit diagram? Because we now know what our Thevenin is. So what does our circuit look like? Because remember, our Thevenin was not actually negative, so we can, but that's fine. Let's draw our Thevenin circuit. Plus, minus, and then we've got our Thevenin there. Then we've got terminal A, terminal B. What was our Thevenin? It was minus 16.6 ohms, and now we know Vthevenin is 2 volts, and that is the complete example. So this gives me Vthevenin. I have R Thevenin. I have my complete Thevenin circuit using a quick method. On the next slide, I'm just going to go through a more conservative, let's call it conservative, method of actually finding Vthevenin. In the next couple of slides, I'm just showing an alternative or a more elaborate way of doing the same example. So just for the interest of time and video size, I'm not going to do a whole video on it. So each slide clearly step by step explains the whole procedure. So this I'm going to leave up to you, and you can work through the slides and through the video. Its PDF is available, and on the video you can pause in between if you want to look at it. But the slides are there for you to look at and follow the example. So this is just a more conventional method, strictly applying mesh analysis or node analysis in order to find the Thevenin equivalent circuit of the example that we just did.